Hello everyone, Professor Dustin here. This video is going to be an introduction to harmonic motion, or oscillations is the other word that goes with this topic. This is basically an application of the stuff we've been doing this semester, conservation laws, Newton's laws, kinematics, to a wide variety of phenomena. Actually, when it really comes down to it, so many things in the universe can actually be described in the natural world and in the human world by harmonic motion of one kind or another. So it's oscillations, and that means that it's stuff that happens over and over and over. Frequently, it's stuff that happens exactly the same over and over and over, but it can also be things that change gradually, where the amplitude increases, the period increases, frequency increases, anything like that can also be described via harmonic motion. The equations are just a little more complicated. So the deal with harmonic motion is that so many things in the natural world can be described this way. I just threw up a list of things that I just thought of off the top of my head, but there are so many others. So planetary orbits. When a planet orbits another object, like a planet orbits the sun, that's harmonic motion because it's happening over and over and over. That's in 2 dimensions, but it still is harmonic motion. Waves. When you get to physics 2, you're going to be talking about waves, both electromechanical, electromagnetic and electromechanical. And so that's a key topic that's going to take from this class into physics 2. Molecules and chemistry. So we model molecules and atoms as essentially balls with springs attached to them, and those are oscillating back and forth. And so that's an example of harmonic motion, and so we use that to model molecules, and that's how the world of chemistry is described via these little vibrating atoms. Also biological processes, not only just like sort of the daily motions or the second-by-second motions that organisms go on to, but also because biology is basically controlled by chemistry, all the stuff about modeling atoms over here also works when you talk about biology. Guitar strings, music, right? So music is harmonic motion of sound, and that sound is produced by things like guitar strings, or striking a piano, or a drum, or playing into a flute. Those are all examples of harmonic motion via oscillations and vibrations. And of course, fundamental physics. So the little particles that we understand, the fundamental universe in electrons, protons, quarks, that kind of thing, they are all little oscillators. We describe them as little oscillators that are bouncing back and forth. And so that's an example of harmonic motion. So all of these things are all examples of harmonic motion. And this is why we really want to tackle this subject, because it's so vast and so many things can be described using oscillations. Obviously, we're going to start very simple, talking about springs, because that's the sort of characteristic thing we've been playing with. But as soon as you get away from thinking about springs, you can do all these different kinds of things. So it's really a key topic for us to take all the conservation of energy, Newton's laws and forces, and all this stuff and stick them into one sort of application which can be used in a lot of various areas. So that's what we're going to get into in this class. Okay, so before we get into the mathematics of harmonic motion, let's just talk some of the basic language and variable type things that we need to do. Let's first just get a picture of something moving in harmonic motion. So here's going to be a spring with a block attached to it like that, and I'm going to pull the block. It's attached to like a ceiling or something. I'm going to take the block, pull it downwards, and let it go. And what I want to do is I want to plot the motion of that object over time. So I'm going to plot the position as a function of time. So time is going to be there, position is going to be there. And let's pick its current position as the origin. So it starts at x equals 0. I pull it down some distance, right there, and then I let it go. And so what's going to happen when I let it go? It is momentarily at rest, but as soon as I let go, the spring is going to pull it upwards. Presumably the spring is strong enough to pull against gravity, because here's the equilibrium position. It wants to go back to it. So I let go. The spring starts pulling on it. It pulls harder and harder and harder. Of course, it actually is pulling less and less hard, but it's adding more and more energy to it, because from the potential energy of the spring is being transferred into the kinetic energy of the block, and it's actually moving faster as it goes up. So faster and faster and faster, crosses x equals 0, and then starts to slow down, because of course the spring is going to push backwards as soon as it crosses x equals 0. So crosses x equals 0, slows down, hits some maximum value at the top, and then the process happens again in the downwards direction. So you probably know what that looks like. It's going to look like a sine or a cosine curve. Specifically, because I pulled it down and it starts in sort of a negative position, it's going to look like this, right? And it's going to repeat forever and ever and ever. In this case, this is basically an object which is going to bounce up and down forever, because I haven't included things like air drag or whatever. So a couple of basic ideas about this curve. It is a sine wave. It's not quite a sine wave, right, because the sine would start here at 0, and it's not quite a cosine wave because the cosine would start up here, but it's some kind of trigonomic function. So basically how we describe these waves is we describe them with an amplitude and with a period or a wavelength. So the amplitude is here. It's how far away from the origin the object gets. That's what I set at the beginning when I pulled it down, is I set the amplitude. And of course the amplitude is the same up here, so even if my picture is not great, the amplitude is going to be the same. And then this object has a period too, which is the period of time it takes for the motion to repeat again. And the way that I've drawn it, it looks like it's one complete period, starts here and ends there. And we usually label that with a big capital T for period. And so that's the period of time it takes to make one oscillation. So this is a unit of time, and this is a unit of displacement in this case from the origin, so it would have a unit of length. Now, of course, there's also, as long with time, there's also a wavelength associated with this wave, but it has to do with the speed of the wave to tell you what the wavelength is. So yes, it is a wave because we think of it like a wave, but typically when we think about oscillations as in springs, it's not clear that there is anything waving here. So we will typically talk about the period. More usual is to talk about the frequency of this thing. So the frequency is the inverse of the period, meaning the period is like it takes 10 seconds for something to happen. The inverse of that is the frequency. That's how often it happens. We will usually call that F for frequency, and it is 1 over the time. So if the time is measured in seconds, then the frequency is inverse seconds. Those are hertz. There's another variable that's associated with this, and that is angular frequency. So angular frequency is the word sort of probably makes you understand. It's a cycles per second measured in radians instead of measured in simply inverse seconds. And so the angular frequency is designated omega, and it is 2 pi times the regular frequency. So this unit is 1 over seconds, and the unit for this guy is radians over seconds. We will probably use both of these notions, but probably omega is the one we're going to use more oftenly because that's actually the thing that's in SI units. Remember, the radians are actually our SI units. Keep in mind that this omega is not obviously related to the angular velocity that we've been dealing with in class, but you actually can find a relationship between it and the regular omega from our angular velocity and angular momentum class, and I will have another video that will talk about that. Okay, so this is the initial setup for how we measure things about the wave and how we sort of talk about these harmonic oscillators. I will say just one more thing about what's going on with this shifting, meaning that this is neither a cosine nor a sine. Actually what it is it's either one of them shifted by a single amount. So if I actually took this point right here and shifted it backwards an amount, and then typically that variable is called phi, which is called the phase shift, I would get a sine function, right? So what that's saying is that this is a shifted sine function. So I'm just guessing at the moment, but I think that if I wrote down an equation for this, it would probably look something like the following. Probably be a sine omega t minus phi. And it could be plus phi. I'm not thinking very carefully, but where that phi is that value. Right, so what I did is I took a sine function. The omega is the frequency, the angular frequency, the time is the time, the a is the amplitude, and this tells you the shift so that I don't have to start the sine function right there at 0. I can start it there and then shift it backwards to get back to the sine. So this is just a guess, but this is sort of the character that we have for these functions. And we are very shortly going to see where this function comes from and how it can be used to describe objects in the real world. Okay, so now we want to try to apply some of our physics knowledge to the situation of the horizontal spring. So I turned it horizontal to get rid of the force of gravity, clearly, because this is going to be easier to deal with. So obviously we've done things with springs already. Specifically, we've measured the amount of energy stored in the spring, and we've used that to like launch things and figure out how fast they're going or figure out how high they go and things like that. But that was really only looking at the initial and the final states of a system, not really what the spring is doing, over all time at specific times, which is what that plot was showing, right? So in order to sort of reproduce that plot, I need a way of describing the position of the box on the spring at every moment. And so we really needed to do Newton's laws for that. So that's the calculation I'm going to do now. So I'm going to start with the free body diagram. The free body diagram for this thing could almost not be easier in the position that it's in right now. So I'm going to set that initial position right there. I'm going to set that to be x naught, and we are going to call that 0. Remember, typically we do like to set the equilibrium position of the spring to be 0 because it makes the calculation simpler. And then I'm going to displace it this way initially before I let it go and let the spring take over its motion. So at that point, there's only one force acting on the spring on the block, and it's the spring force going that way, Fs. Now, of course, there are two other forces, gravitational force Fg and the normal force Fn. But in this case, we actually don't care about those guys. They're just going to be balanced out against each other because the block is not accelerating in the y direction. So we only have a spring force here. Okay, so if I want to write down Newton's second law, that's going to be pretty easy. Some of the forces, let's take it as the x direction. So let's label this guy as x. Is going to be minus kx. Check that to make sure the signs work. Remember that thing about springs, tricky to get the signs right. Pushing this way means that the x is negative, so that means negative, and that negative makes the spring force positive, and that's pushing that way, spring force is positive. Good, that makes sense. Okay, I'm going to write this as ma, and this is the equation which is governing the motion of the block. Now notice, this is not an equation we can easily solve, right? We have x over there, and we have a over there. So it's not totally obvious how I can get like a position as a function of time. Notice that like we could try to do some of the things that we did to derive the kinematic equation. So remember, for the kinematic equations, we had a is constant. A constant acceleration, that is the derivative of the velocity. So what we could do there is move the time over and integrate both sides and end up with the position as a function of time. Eventually would get down to x of t is 1/2 at squared plus v naught t plus x naught. That was the end result of that calculation. Well, we'd like to do something very similar, but we can't do it in this case because our force is not constant. It depends on x. The best we could maybe do is keep trying to rewrite the a so that we have an x over here, so then maybe we could solve it. Remember, a is the second derivative with respect to x. So I could write the following. I could write minus kx is m d squared x over dt squared. Remember, that's really not a square, right? It's a second derivative, just a language thing. I say square, I can't help it. So this is the equation that actually governs the motion of the block. It's Newton's second law. This is called a differential equation. It's got a derivative, in fact, two derivatives on one side and a linear term on the other side. This is not something that I think you guys know how to solve. You learn how to solve these things in a course called differential equations. Of course, I don't think you have differential equations, so I'm not going to ask you to solve this thing. But we can check solutions. I can propose a possible solution to you. X is a function of whatever the function is, and you could plug it into this equation and determine if it actually is a solution to it. So that's actually how we're going to solve this equation. We're going to prove that we have solutions instead of actually finding the solutions. First thing let's take our original positions as a function of time in kinematics, plug it in there, and see if it actually ends up being a solution. This is the form of the thing that I want, so let's check it. So the way you check it is you put it into both sides and then check to see if they are equal. Probably what you're going to do is end up having to set some constants equal to each other to make this work. And actually what I'm going to do is I'm not going to use this. I'm going to propose another version of this and say, okay, well, maybe it's probably not like a and v naught, right? But maybe it's like some constant t squared plus some other constant times t plus c, where a, b, and c are arbitrary constants. So maybe this will solve that equation if I pick a, b, and c appropriately. Okay, so let me try that. The first thing I'm going to do is write the left-hand side, because the left-hand side is going to be easy. Minus kx is minus k just times this whole function. at squared plus bt plus c. Cool. Now I have to get the right-hand side of this equation. So this is the left-hand side. Let's call that left-hand side. Now I want the right-hand side. That means I need to take two derivatives of this guy to figure out what the second derivative is. So let's take one derivative, dx dt. So if I hit this with the derivative, pull a 2 out, I get a 2a times t. That's that term. Next term, hit that with the derivative, kills the t to the first down to t to the 0 plus b. C is constant, hit that with the derivative, and it goes away. Okay, so that's one derivative. Now I have to take a second derivative. That's just taking the derivative of this thing again. Getting simpler, fortunately. So hit this with the derivative, I get 2a, because the t to the first goes away, and the b vanishes because it's constant. Okay, so that is my that's my second derivative. Let's write down the right-hand side carefully. Right-hand side is equal to 2m times a, right? 2m times a, because I have a mass there. And so if I'm going to make the left-hand side equal to the right-hand side, actually there's negative signs. Sorry, I got the negative sign, so we're good there. If I want to make the right-hand side equal to the left-hand side, I'm going to write them down and see if they are equal. So I'm going to write minus k at squared plus bt plus c is equal to 2m times a. Okay, so could those, question mark, right, might not be equal. Could those two things be equal? Well, first of all, it has to be equal for all time. So I can't have like those related to each other or those related to each other because there's no time over here, right? If I don't have any time over here, then I better like make sure that these terms aren't there, right? I have nothing over here to match those guys. But I'm setting constants. So what I'm going to say is, okay, there's no t squared over there, so that means that I better have the constant a be 0. That had better be true because I'm never going to match these two sides without that being true. Also, the b has to be 0 as well because there's no t over there, so I need to set b equals 0 as well. So maybe up here, if I set a 0 and b 0, maybe c, constant position, will satisfy this, right? What that means, okay, so if I said those two things are 0, that means what I'm implying is that minus k times c is maybe equal to 2m times a. So that could be a solution. So maybe this does solve this equation as long as I use the constant c is 2ma over k. But of course there's a problem with that, which is I've already set the a to be 0. So this thing is actually 0, which means c is 0, and the only way this can be a solution to this Bragg equation is if it's 0. So clearly that is not the right answer. So what we're going to have to do is find a different function which does actually satisfy this relationship. And I'm going to give you that and show you how to check that it actually works. Okay, so what's the function that I want to check? Well, I gave you the function in the last projector up here, which is the sine function. So we're going to check that a sine omega t plus phi is a solution to this equation. So remember, a solution means I can plug it in there, I plug it in there, and I can pick the constants. So here I have three constants, a, omega, and phi. I can pick those three constants such that this equation satisfies our Newton's second law. So let's see how that works. Again, I'm just going to do left-hand side and right-hand side. So left-hand side is just going to be minus k times x, so it's just minus k times a sine omega t plus phi. So nothing to do there, really. On the right-hand side, I have to take some derivatives to get to that second derivative there. So first, let's take a derivative, dx dt. So a is a constant, so that doesn't get hit by the derivative, but the sine function does get hit by the derivative. So remember that the derivative of sine is minus cosine. In my head, I have to like think of the sine and think of the cosine to make sure I get the signs correctly. It's going to be minus cosine omega t plus phi. And then just remember that you have to do a chain rule on the sine omega t plus phi. I'm taking a derivative with respect to t. T is in there, so I need to take the derivative of what's inside here, omega t plus phi. Phi is a constant, so I'm just going to get an omega out of it. Right there's the whole thing. So I get minus a cosine omega t plus phi times omega. I should probably rearrange the omega, put it down front, whatever. I want to take one more derivative, so let's do that. d squared x dt squared. So again, I only have to take the derivative of the cosine. The cosine derivative of cosine is positive sine. And again, I have to take another derivative of the inside here. So let's collect the a and the omega first. That's negative sign is going to stay. It's going to be a sine now. Omega t plus phi. And then I need to take another derivative of the inside. That's another factor of omega, so I get omega squared right there. So that's the second derivative. So then to write the right-hand side, I just take that and multiply it times the mass. And let's put the negative sign in there, so a m omega squared sine omega t plus phi. Cool. So I got the right-hand side and the left-hand side written down. Now I can go ahead and check to see if they are equal to each other. So I'm just going to set them equal to each other. Minus k. Sorry, I forgot an a sine omega t plus phi. Equal with a question mark, because I'm checking, to minus a m omega squared sine omega t plus phi. Cool, so we want to determine if these two things can be equal to each other, and at first glance it looks like things are going to go pretty well because we have a sine of omega t plus phi in both sides. So that's the trick here, right? The trick is that take two derivatives, sine goes to cosine, but back to sine, and I need there to be the same as the original function. Other things that do that are cosines, so I didn't just have to use a sine. Exponentials do that, so there's other ways of solving this equation, but the sine happens to be the nice one that I like. So basically we can now work on solving this thing. I'm going to cancel the sine on both sides. That seems reasonable because it's the same on both sides. I also have a factor of a on both sides, which is cool. And I have a plus sign on both, and a minus sign on both sides, so I'm going to cancel that. So what I have left over is I have a k, that's the spring constant, is m omega squared. Cool, so remember my problem, I want to set a, omega, and phi such that this equation is solved. It looks like I can totally do that. What I have to do is set k over m equal to omega squared, or omega is the square root of k over m. Cool, all I have to do is that, and then this is a solution to the spring equation. So I've solved the spring equation by guessing a solution form and then saying that, oh, if I pick omega, k over m, square root of k over m there, then it does indeed solve that. Now notice that I didn't have to set a or phi. So it doesn't matter what the value of a or phi is, this equation is going to be satisfied. Now when we actually do problems, we are going to be setting a and phi, and that's one of the things that I'll talk about in class. But at the moment, we just want to notice that we can do anything with this equation we like as long as we say that the angular frequency is going to be the spring constant divided by the mass.